Okay, hello everyone. The intent of this screencast is to wrap up some of the unfinished business from Lecture 14 on using the finite differencing equations to solve the two-dimensional conduction heat equation. So to kind of recap where we were in Lecture 14, we proposed that, as an example, we could take a square domain with 4 elements in the x direction, which we denoted using an I index, 1, 2, 3, 4, and 4 elements in the y direction, indicated by the j index, 1, 2, 3, 4, to give us what we called our mesh, or our nodal network. From this, we constructed 3 tables that are key to sort of the bookkeeping aspect of solving the problem. The first we called the node locations table, where the first column is composed of the ascending n indices of each node, so 1, 2, 3, 4, 5, 6, 7, 8, counting up from left to right in ascending rows. And then the next 2 columns are the respective I and j indices of those same nodes. So element 1, or node 1, has an ij index of 1, 1, shown by these 2 tables. The boundary nodes table is constructed of all of the nodes n such that they lay on the outer edges of the domain. So in this case, this would consist of any nodes that have an I index of 1 or 4, more generally, right? 1 or n sub x. And any node that has a j index of 1 or 4, though in general this 4 will be replaced by n sub y. Right, if your element has an I or j index that's at either the beginning or the end of your domain, that means it's laying on an edge. And so you'd put it in this boundary nodes table, and the next column would contain the known temperature at that node, since we are proposing that the temperatures are known everywhere on the boundary of this domain. Finally, right, we have this last table we call the interior nodes. This consists of these 4 nodes on the inside that do not reside on a boundary, and thus we do not know the temperature. So the way we get this is simply take this exhaustive list of all of our nodes, 1 through 16, and eliminate any numbers that are in this first column of our boundary nodes table. Whatever's left over is what we're looking for ultimately in the problem. Right, so we covered in lecture, right, and the screencast from that lecture is available on the icon site or the associated YouTube channel. We covered how you can begin to construct what's known as your coefficient matrix to solve this problem. Right, the end goal here is to construct a matrix system of equations that looks like this. A times t equals b, which will then solve using an inversion of this A matrix. So to start this process, right, we said that you can build the A matrix by hand for problems that are very small like this one, but as the problems get larger and larger and larger, it becomes impractical to build the equation by hand or to build the system of equations by hand to put into matrix form. So it's a lot easier to use some simple tricks in MATLAB or a similar programming language to speed the process up. So the way we did this in class was say we'll define a row vector. We'll call this FR for first row. And this was equal to -4, 1, 0, 0, 1, 0, 0, 0, 0, and let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So this would be the very first row in our A matrix before we begin to shave our A matrix down to something more manageable. This is valid only for this 4x4 problem, right, which is why it has a total of 16 elements, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. More generally, you would write this, and I'll use MATLAB notation here, as -4, 1. Then a command zeros 1 by nx minus 2, 1, zeros 1 by nx times y minus nx minus 1. So what this is doing, right, here we have this -4 and this 1 followed by the number of intervening zeros, in this case, right, in the case we wrote above, nx is equal to 4, so nx minus 2 gives us those 2 zeros, followed by a 1, and then however many zeros are required to fill up our row so that we have the number of elements in that vector, same number of elements in that vector as we have elements in our whole domain. We then said we're going to start building our A matrix using this nifty trick in MATLAB called construction of a toplets matrix. So if we give the command toplets of fr, where fr is this row vector that we've just constructed, what it's going to do is spit out this giant square matrix. In this case, that matrix is going to be 16 by 16, or the number of total elements by the number of total elements. This is too big, right? We don't actually have 16 unknowns, so there's no reason for us to have a 16 by 16 matrix in our system of equations. That's fine. Our approach here, right, rather than building our A matrix piece by piece, is to make a giant A matrix and shave away the elements that we already know something about. So we have our giant A matrix, and our next step was to essentially remove all rows that correspond to nodes that are on the boundary. And in MATLAB, right, this command was say that A of, well, we'll go ahead and define an intermediate vector here. We'll say n boundaries is equal to our boundary nodes table, where we're taking just the very first column. So this notation here, right, this colon means all elements in this case in the vertical direction. So this would give us the first column of our boundary nodes table, which would be, right, the values of n for all nodes that are on the boundary of our domain. So what this command is doing is it's saying take that first column and make it its own vector. So this n boundaries will simply be 1, 2, or will be a column vector that looks like 1, 2, 3, 4, 5, 8, so on and so forth. So then we're going to say A and boundaries and colon in the second index is equal to empty square brackets. What this is going to do then is take every row that corresponds to one of these values of n and delete it. So what this will give us then is a matrix that looks like so. So this is where we left off class on Friday with lecture 14. And what we have here is, right, a system of 4 equations for our 4 unknowns, which is a good place to be. Our problem, however, is that, right, our A matrix now is a 4 by 16 matrix. That is 4 rows high by 16 columns. And our unknown, right, is 16 by 1, and our B vector here is 4 by 1. So the matrix math here works out fine. You can multiply this 4 by 16 by 1 and get out a 4 by 1, but this A matrix, right, is not square. And as a result, we cannot invert it. So the way we're going to get around this problem is by, once again, saying we know something about a bunch of these temperatures already. right? Those temperatures that are on the boundary are known conditions of the problem. We don't need to solve for those. So, right, we can take those and move them over to the right-hand side of the equation. Now, the way we do this is a little bit tricky. It requires you to sort of understand what's going on when we do matrix multiplication. Essentially, what's going over here on the right-hand side is this first column multiplied by T1, plus this second column multiplied by T2, plus this third column multiplied by T3, so on and so forth. So what ends up on the right-hand side is a weighted sum of all of the columns in our vector or matrix on the left-hand side. What this means for us is that we can subtract things over simply by taking, for example, this temperature or this column, multiply by T1 and take that entire quantity over to the right-hand side and then strike it from our A matrix and our list of unknowns. Okay, so what this is going to look like is in MATLAB is execution of a for loop, and this should be something that you're familiar with from programming. That you're going to you're going to loop through that vector we defined called n boundaries. So it's going to step through every single node that sits on a boundary. We'll say n is equal to, so here let's make this a bit more formal. We'll say 4. Say say nb to 1 to the length. What this will do is it'll step one at a time through that list of boundary nodes. We can say n temp, or a temporary n, is equal to n boundaries, and we'll pull out that corresponding value of n, and then we'll say t temp, that is the known temperature at that boundary, is equal to boundary nodes B2. So what this is doing is it's stepping one at a time through the rows of this table right here. It's pulling out this value of n, and it's pulling out the associated known temperature. Okay? Next, we're going to say B is equal to B minus T temp times A. So remember this notation here, okay, with this colon, comma, n temp, means it'll look up that value of n, cycle through over, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14, 15, and 16, right? So each column of A corresponds to a value of n associated with node n. So it'll step through each boundary node, find the value of n, pull out that specific column of A, multiply it by the known temperature, and subtract it from the right-hand side. Note, before you execute this loop, you're going to need to start your B array by first saying that it is equal to a vector of zeros, okay? And then we'll go ahead and use this recursive loop to continue to subtract quantities from that B. So this constitutes the for loop. Once that's done, you're going to want to go back through and remove all of those columns from the A matrix that we just moved over to the right-hand side. So what this is going to amount to is striking 1, 2, 3, 4, 5, 8, 9, 12, 13, 14, 15, and 16 out from A, right? At this point, they've all been moved over to the right-hand side, so they have no business remaining on the left-hand side. And the way you do this is with the MATLAB command A colon and boundaries. Once again, equal to empty square brackets. So similar to before, right? This will now find essentially, it'll remove any row that's associated or any column that's associated with a boundary node. The reason you don't want to do this inside of your for loop, okay? This is something that people tend to try to do. The reason you want to avoid that is because if you're stepping through, let's say you start out at boundary node 1, you move that over to the right-hand side and you delete column 1. What happens then is MATLAB is going to shift all the remaining columns over so that node 2 becomes, or column 2 becomes your new column 1. So that when you then move on to the next boundary node, n equals 2, unless you are really careful with your bookkeeping, it's easy to accidentally remove column 3 from your A matrix. So it's easiest to simply move everything over and then go through and delete everything in one fell swoop. So where do we stand at this point? Once we've completed this section of our MATLAB code, we're going to be left with this little chunk of our A matrix. So I'll go ahead and copy that down. -4, 1, 1, 0, 1, -4, 0, 1, 1, 0, -4, 1, and 0, 1, 1, -4. So at this point, our matrix system of equations looks like this. Okay, why is this a better situation to be in? Well, because now our A matrix is 4 by 4, meaning it's square and thus invertible. We have, for our T matrix, our T vector here, only the 4 unknowns that we're looking for, and our B vector is going to be some combination of our temperatures at the boundaries. Okay, where that combination will be dictated by the way things go in this for loop here. So at this point, finding T, right? At this point, we don't actually have T, so writing it out as this vector is a little bit arguable, but the way we would actually find this T then is T equal to, right, A inverse B. Now, you may have to do a little bit of digging in the MATLAB documentation as to how to solve a matrix system of equations doing this. It's really quite easy, but once that's completed, you'll get out a vector that contains T at the interior nodes. So the problem is solved at this point. What remains is to reconstruct the entire domain of temperatures from these things that you've just solved for, plus the things you already knew. And this is where this very first, or the remainder of these tables we put together at the beginning come in handy. What I recommend doing is taking your interior nodes table and adding a second column to that, so that now you have N and you have the temperature at that node. So we'd have T6, T7, T10, and T11. Then I recommend taking this entire table and simply pasting it onto the end of your boundary nodes table, so that what you'll have is, here, let me grab the right pieces. what you'll have is a complete list of every node in the domain plus the temperature at that node, where the first chunk of these, right, these come from, or where all of these come from the boundary conditions. And then these come from the solution to the problem. Then you can go ahead and loop through, right, the rows of your new augmented table here. And then for each value of n, you can look up the I, j index and plug in your results into a matrix form of T. So T, I, j equal to T sub n. And at that point, what should come out is a matrix, a 4x4 matrix of temperatures, or an nx by ny matrix of temperatures that contains, that you can then plot using things like the contour function in MATLAB, the surface function, or the filled contour. And so this wrap up here should give you all the information you need to finish the solution to the heat equation on a two-dimensional domain, including the solution to the homework number 4 problem.